Welcome to Chem Talk. Ever feel like you're trying to count, I don't know, grains of sand on a huge beach? Impossible, right?
Totally. Well, today we're diving into Chapter 10 from your textbook, The Mole and Conversion Calculations.
Yeah, think of this as your, ultimate power-up for chemistry calculations.
Exactly. We know tackling numbers, formulas, it can sometimes feel like you're trying to decode alien instructions in a sci-fi movie or something.
Or like a really confusing video game tutorial.
Right. So our mission today is to make this whole mole concept and the conversions super clear. Maybe even, dare I say, kind of fun.
We can try. We'll definitely connect it to things you might recognize from games and movies.
We're going to unpack what the mole actually is. And nope, not the furry little guy digging up your lawn.
Right. It's about how chemists count atoms and molecules, which are unbelievably tiny.
And then how we use this mole thing to switch between counting particles, figuring out their mass, and even measuring gas volume.
Your textbook has that great analogy, right? Ordering sand. You wouldn't order it by the grain.
No way. You'd order, like, a cubic yard or something. You need a bigger unit for tiny things in huge amounts.
And that's exactly what the mole does for atoms and molecules in chemistry.
Precisely.
Okay, so 10.1 in the book talks about Avogadro's number. Let's dig into why we even need such a big counting unit.
Well, think about it like pixels on a giant screen in your favorite video game, trying to count every single one.
Forget it. Impossible.
That's kind of what it's like with atoms. There's just so many. Counting them one by one is a non-starter.
So enter Amedeo Avogadro.
Yep. He didn't discover the number itself, but it's named in his honor. The idea is simple. Just like a dozen always means 12.
A mole always means this one specific, absolutely massive number.
6.02 times 10 to the 23rd. That's Avogadro's number. It's our go-to unit for counting particles.
And the scale is just mind-blowing. Your book mentions a single drop of water.
Yeah, it has something like 10 to the power of 22 water molecules in it.
Trying to count that high, it's like trying to defeat an endless wave of enemies in a game. It would literally take trillions of years.
Exactly. So the mole gives us a way to talk about these quantities without our heads exploding.
Now, the book says the mole counts representative particles. What does that mean exactly?
Good question. It depends on the substance. If you have an element like iron or carbon or helium gas, the representative particle is just the atom. So a mole of iron is 6.02 by 1023 iron atoms.
Okay, but what about things like water, H2O?
Well, water exists as molecules. Groups of atoms bonded together, so do elements like hydrogen, nitrogen, oxygen. They come as H2, N2, O2. For these, a mole is 6.02 by 1023 molecules.
And then there's the third type, ionic compounds, like salt, NCl.
Right. For ionic compounds like sodium chloride or calcium nitrate, KNO3-2, we talk about formula units. So a mole of salt is 6.02 by 1023 NaCl formula units.
But the key is, whether it's atoms, molecules, or formula units, 1 mole is always 6.02 by 1023 of them.
Always. It's the universal counting number for chemistry. Like, having the same number of players in different game lobbies, even if the games are totally different.
Cool. And the book mentions the fun fact.
Well, yeah. Chemists have kind of playfully adopted the animal mole as an unofficial mascot.
And there's Mole Day, October 23rd.
Yep, probably 23, get it? Because of the 10 to the 23rd. It's a bit nerdy, but fun.
Definitely nerdy. Okay, moving on to section 10.2. Conversions between moles and atoms. We know what a mole is. Now, how do we actually use it?
Well, like your book says, using moles just makes life easier. Instead of writing out these gigantic numbers with huge exponents all the time.
Which is just asking for typos.
Exactly. We use moles, and the key is that conversion factor we just talked about.
1 mole equals 6.02 by 1023 representative particles.
That's your golden ticket. It lets you switch between counting particles and counting moles. Think of it like exchanging gold pieces for silver pieces in an RPG. You need the exchange rate.
Okay, sample problem 1 in the book asks, if you have 4.72 by 1024 carbon atoms, how many moles is that?
Right. So you have the number of particles and you want moles. Use the conversion factor.
We need to divide by Avogadro's number, right?
Spot on. Take your 4.72 by 1024 carbon atoms and divide by 6.02 by 602 by 1023 atoms per mole.
Let's see, calculator time. Roughly 7.84.
Yeah, about 7.84 moles of carbon. And notice, since we started with more atoms than Avogadro's number, our answer is more than 1 mole. Makes sense.
Okay, that seems straightforward. But what if the question is trickier? Like finding the number of hydrogen atoms inside a bunch of water molecules.
Now you need the chemical formula. That's your map. Water is H2O. What does that tell you?
2 hydrogens for every 1 oxygen. So 2 hydrogen atoms per molecule.
Exactly. So if you know how many water molecules you have, just multiply by 2 to find the total hydrogen atoms.
Like checking a crafting recipe in a game, you need 2 iron ingots and 1 stick to make a sword. That kind of ratio.
Perfect analogy. It's all about those ratios in the formula.
Okay, sample problem 2 puts this together. It says you have 4.89 by 1025 oxygen atoms, and they're part of sulfuric acid, H2SO4. The question is, how many moles of sulfuric acid is that?
Okay, this is a good one. It's a 2-step process. First, look at the formula, H2SO4. How many oxygen atoms in one molecule?
4. H2SO4.
Right. So first, figure out how many H2SO4 molecules you must have to contain that many oxygen atoms, since there are 4 oxygens per molecule.
You divide the total oxygen atoms by 4. So 4.89 by 1 over 25, 4.
Gets you the number of H2SO4 molecules, which comes out to about 1.22 by 1 over 25 molecules.
Okay, step 1 done. Now we have molecules and we want moles.
And how do we go from molecules to moles?
Divide by Avogadro's number. So 1.22 by 1 over 125 molecules, 6.02 by 1 over 23 molecules small.
Should give you about 20.3 moles of sulfuric acid.
Wow, okay. So use the formula for the atom ratio, then use Avogadro's number. Got it.
Right, next up, section 10.3. Molar mass. So far we've been counting particles, which is great conceptually, but in the lab.
You can't exactly count atoms one by one. You need to weigh stuff out.
Precisely, and that's where molar mass comes in. It's the bridge between moles, our counting unit, and grams, which we can measure on a balance.
So what is molar mass technically?
It's defined as the mass, in grams, of 1 mole of a substance's representative particles. The units are grams per mole, or gemole.
Okay, grams per mole. And how do we find it? Do we have to memorize a bunch of values?
Nope. Even easier. For individual elements, the molar mass is right there on the periodic table. It's usually the decimal number listed under the element symbol.
Ah, the atomic mass number, but in grams.
Technically, the number on the table is the average atomic mass in atomic mass units, AMU. But numerically, it's the same value as the molar mass in grams per mole. So lithium, Li, is about 6.94 AMU, which means its molar mass is 6.94 GMol.
Okay. Zinc, Zn, is 65.38. So 65.38 GMol. Gold, Au, is 196.97. 196.97 GMol.
It's like looking up the value or weight of a specific resource in your game inventory.
Exactly. The periodic table is your ultimate cheat sheet for molar masses of elements.
But what about compounds, like CO2?
Again, the formula is key. CO2 means 1 carbon atom and 2 oxygen atoms per molecule. You just add up their individual molar masses.
So carbon is about 12.01 GMol. Oxygen is about 16.00 govern GMol. So it's 1 12.01 plus 2 16.0.
You got it, which equals 44.01 GMol for carbon dioxide. Nice. The book has a sample problem for calcium nitrate, KNO3 too. Looks a bit more complicated with the parentheses.
Just gotta be careful counting the atoms. The formula K, NO32, means we have 1 calcium K atom.
Oh.
The subscript 2 outside the parenthesis applies to everything inside. So 2 nitrogen N atoms.
Right, 1K at 2N.
And 2 times 3, which is 6 oxygen O atoms.
Ah, okay. 1Ka, 2N, 6O. Then we just add up their molar masses.
Yep, 1 times K's mass plus 2 times N's mass plus 6 times O's mass, using the values from the periodic table. 1 by 40.08 plus 2 by 14.01 plus 6 by 16.0.
Comes out to around 164.90 GMol for calcium nitrate.
Perfect. Calculating molar mass is just careful addition using the formula and the periodic table.
All right, section 10.4, conversions between moles and mass. This feels like where it all connects. We can finally link the count of moles to something we can actually weigh mass.
This is super practical. Like the book example says, if an experiment needs, say, half a mole of a chemical, you don't count out the particles. You use the molar mass to figure out how many grams to weigh.
So molar mass is the conversion factor between moles and grams.
Exactly. It's expressed in grams per mole, GMol. If you have moles and want grams, you multiply by the molar mass. If you have grams and want moles, you divide by the molar mass.
Kind of like knowing the exchange rate when you're trading resources in a strategy game, like wood for stone.
Good analogy. You need that rate, the molar mass, to make the trade between grams and moles.
Okay, sample problem time. Find the mass of 0.560 moles of chromium, Cr.
First step.
Find chromium on the periodic table, Cr atomic number 24. Molar mass is about 52.000 mole.
Great. Now we have moles, 0.560 mole, and we want mass grams. So
Yeah.
we multiply.
Yep, 0.560 moles times 52.00 grams per mole. Moles cancel, equals 29.12 grams of chromium.
Exactly, 29.1 grams with sig figs.
Nice. Okay, let's go the other way. Convert mass to moles. Example, determine the number of moles in 2.81 grams of copper 2 hydroxide, COH2.
Okay, what's the first thing we need here? We have grams, we want moles.
We need the molar mass of COH2.
Right, so 1 copper key plus 2 oxygens O plus 2 hydrogens H.
Okay.
Add them up.
Copper's about 63.55, oxygen's 16.00, hydrogen's 1.01, so 63.55 plus 16.00 plus 1.01 gives us about 97.57 joule.
That's right. Now you have the mass, 2.81 gram, and the molar mass, 97.57 joule to get moles.
Divide the mass by the molar mass, 2.81 gram, 97.57 joule cancel. Gives moles. About 0.0288 moles.
Perfect. See, once you have the molar mass, converting between grams and moles is pretty straightforward multiplication or division.
Okay, this is building nicely. Section 10.5 is conversions between mass and number of particles. So now we're combining the last two steps, going all the way from grams to atoms or molecules or vice versa.
Exactly. This is where the mole really shines as that central connection point. You can't directly convert grams to particles. You have to go through the mole.
So it's always a two-step process. Mass to moles using molar mass, then moles to particles using Avogadro's number.
Right.
Or the other way around.
That's the path. Mass, moles, or particles. It's like a multi-stage quest in a game.
Yeah.
You can't teleport directly to the final boss. You have to complete the intermediate levels first. Moles is that crucial level.
Gotcha. Let's try the sample problem. How many molecules are in 20.0 grams of chlorine gas, Cl2?
All right, roadmap time. We're starting with grams mass. Where do we go first?
Grams to moles. We need the molar mass of Cl2. Chlorine Cl is about 35.45 joule, so Cl2 is double that, 70.90 joule.
Good. Now convert the mass to moles.
Okay, 20.0 gram divided by 70.90 gmol gives about 0.282 moles of Cl2.
Step 1 complete. Now we have moles and we want...
Molecules. So moles to particles. We use Avogadro's number.
And do we multiply or divide?
Multiply 0.282 moles times 6.02 by 1023 molecules per mole.
Which gives you about 1.70 by 102 under 3 molecules of chlorine gas.
And the book makes a good point. You don't even have to calculate the intermediate mole value separately. You can just chain the calculations together.
Yeah, you could do 20.00, 70.90 to GO, 6.02 by 1023 molecule all in one go on your calculator. Saves a bit of time.
Cool. Now, section 10.6 takes us into gases, Avogadro's hypothesis, and molar volume. So the mole applies to gases too, but volume comes into play.
Yes, because gases are often measured by volume. Think about like filling a virtual reality tank with oxygen in a game, or the volume of air needed for combustion. Volume matters for gases.
And Avogadro's hypothesis is key here. What does it state again?
It says that equal volumes of any gases, as long as they're at the same temperature and pressure, contain the same number of particles, molecules, or atoms.
That's huge. So volume is directly related to the number of particles, but only if temperature and pressure are constant.
Exactly, because gas volume changes a lot with T and P. So to make useful comparisons, we need a standard reference point.
Which is standard temperature and pressure, or STP.
Right, defined as 0 degrees Celsius, that's 273.15 Kelvin, and 1 atmosphere of pressure. Think of it as the agreed-upon level playing field for comparing gases.
And at STP, there's a special volume for 1 mole of any gas.
Yes, that's the molar volume. 1 mole of any ideal gas at STP occupies a volume of 22.4 liters.
22.4 limol. Another conversion factor. Awesome.
It is. It directly links moles of a gas to its volume, but remember, only at STP conditions.
Got it. Sample problem 1. 86.5 liters of hydrogen gas, H2 at STP is how many moles?
We have volume L and want moles.
Mm-hmm.
We use the molar volume 22.4 mole as the conversion factor, so it's going from liters to moles.
Divide. 86.5 liters divided by 22.4 alone gives about 3.86 moles of H2.
Perfect.
Sample problem 2. What volume does 4.96 moles of O2 occupy at STP?
Now we have moles, want volume.
So multiply by molar volume. 4.96 moles times 22.4 lemol equals about 111 liters.
Spot on.
Okay, sample problem 3 brings mass back in. What is the mass of 867 liters of N2 gas at STP? Uh-oh, 2 steps again.
You know it. We have volume, we want mass, we can't go directly. What's the intermediate stop?
Moles, gotta go volume moles.
Yeah, exactly. Step 1, volume to moles.
867 L divided by 22.4 lemol gives about 38.7 moles of N2.
Okay, step 2, moles to mass. What do we need?
Molar mass of N2, nitrogen N is 14.01 gmol, so N2 is 28.02 gmol.
Right, now moles to mass.
Multiply. 38.7 moles times 28.02 gmol equals roughly 284 grams, or about 1.08 kilograms of N2.
Excellent. See how the mole connects volume and mass for gases at STP.
Yeah, it's really the central hub. Which brings us to section 10.7, gas density and the mole roadmap. How does the mole help with density?
Well, remember, density is mass divided by volume, mv.
Yeah.
And we just saw that at STP, 1 mole of any gas occupies 22.4 elards.
Okay.
But 1 mole of different gases has different masses, right? Based on their molar mass.
So if they all take up the same volume, 22.4 liters per mole at STP, but have different masses per mole.
Then gases with higher molar masses will be denser at STP, because you're packing more mass into that same 22.4 liter volume.
That makes total sense. So we can calculate the density of a gas at STP easily.
Yep. Density at STP driller, molar mass in Gmol, molar volume in Lmol, which is 22.4.
Let's try the sample problem. Density of nitrogen gas, N2, at STP.
We just found the molar mass of N2 is 28.02 gmol. So density equals 28.02 gmol divided by 22.4 mol.
Comes out to about 1.25 GL.
Exactly.
Okay, and this mole roadmap the book mentions sounds like a visual summary of everything we've done.
It totally is. It puts the mole right in the center, and it shows arrows connecting the mole to mass, grams via mole
Or
weight,
number of particles, atoms, molecules via Avogadro's number.
and to volume of gas liters via molar volume. But remember, only at STP.
So if you need to convert between any of those outer boxes, mass, particles, volume, you just follow the arrows through the central mole hub.
That's the strategy. It helps visualize the steps needed for any conversion.
Final sample problem uses the map. What is the volume of 79.3 grams of neon gas, Ne, at STP?
Okay, follow the map. Start at mass, grams of Ne, where to first?
To the mole hub, grams to moles using molar mass. Neon periodic table. Molar mass is about 20.18 gmol.
Right, so calculate moles.
79.3 grams divided by 20.18 gmol gives about 3.93 moles of Ne.
Okay, we're at the mole hub. Now where do we want to end up?
Volume at STP, so follow the arrow from moles to volume L.
And the conversion factor on that path is?
Molar volume, 22.4 mole, and since we're going moles to volume, we multiply.
Good.
3.93 moles times 22.4 molar moles equals about 88.8 liters of neon gas at STP.
Boom. You've navigated the mole roadmap.
Phew. Okay, that was a serious deep dive into the mole and all its conversion magic. You listening should really feel like you've leveled up your understanding of how chemists connect the tiny world of atoms to the stuff we can actually measure.
Absolutely. Just remember, the mole is like that indispensable multi-tool in your chemistry toolkit. It lets you translate between the count of particles, their mass, and the volume of gases at STP.
Keep practicing those conversions. They might seem tricky at first, but like mastering a difficult combo in a fighting game, they'll become second nature with practice.
We really hope this Chem Talk helped clear things up and maybe made Chapter 10 feel a bit less like a final boss battle and more like an exciting challenge you can totally conquer. Keep exploring chemistry. It's awesome stuff.
It really is.
And one last thing, a huge shout out to the Geeky Gamer Science teacher for putting together such a great resource that inspired this discussion.